Alright, so welcome to the 19th lecture, and this time we're going to prove the complex spectral theorem. And different from the real spectral theorem, the condition for complex spectral theorem is looser than the real ones. Okay, so first, before that, we need a definition. So for any polynomial in K given by this, we define the polynomial with the input the operator T as a naught gives a naught I, identity map, A1Z is T, and Zn gives Tn. And T to the n is the algebra over the operators, which is T compose, compose n times, okay? Okay. And for a vector space, we have, for a finite dimensional vector space over the complex field, we have that any operator has an eigenvalue. And the proof is based on the fundamental theorem of algebra. So first, let's just construct a list of vectors. So pick any non-zero vectors v, and we consider the list of vectors v, tv until tn of v. This is n plus 1 vectors, which is linearly dependent, which means that there exists a non-constant polynomial such that pt of v gives you 0. Okay, this should be more precisely the 0 vector nv, 0v. Okay, so from here to here is just like, it's just by, right, this thing. It's a constant, non-constant polynomial such that pt of v is non-constant because v is non-zero, right? And for this polynomial, we apply the fundamental theorem algebra. So we can factor it totally, or you factor in something that looks like this, okay? And thus, we just 0v is equal to pt of v, but pt of v, and we change this to pt, gives you t minus lambda 1i, t minus lambda 2i, t minus lambda degree of pi, right? Which is this, c of this applied to v. Now, if this thing goes to 0, then we're done, right? Otherwise, we pass it to this, and so on. But ultimately, right, at some point, eventually, we show that t has an eigenvalue, right? So this is the fundamental theorem for algebra applied to our case, is that any operator over C has an eigenvalue. And we don't have this over the real field, right? Because any real polynomial not necessarily has a root. Okay, so here's the lemma. For an inner product space over K, but in our case we care about C, if W is invariant under T, then W perp is invariant under T star. So the proof is really just one line, okay? There's really just one line. And from the last time, recall that for any inner product space over K, okay, not from last time, from last two lectures, I remember, if I give it any normal operator, we have this equality holds. That is that T and T star has the same eigenvectors. And we're gonna use this fact to prove our complex spectral theorem. And the statement for complex spectral theorem is really just over R changed to over C, and we have the same thing, but instead the equivalence followed by just T being normal. Normal is stronger than self-adjoint, okay? So T is normal if only if there exists an orthonormal basis such that each of them are the eigenvectors of T. And okay, so for this direction, if dimension of v is equal to 1, right, we just pick, it's follows easily. Now, we do the induction step. By theorem, we have an eigenvector, an eigenvalue. We let this lambda denote as lambda n, and we let en, which is normalized as v, a unit vector. Now we consider W the subspace be the span of this en. Well, which is invariant under T because we have this. And the dimension of W is equal to 1. which means that the dimension of W perp is n minus 1. Now, T is normal, implies this is also an eigenvector for T star, right? This implies that T star W is contained in W, saying that W is invariant under T star. By the lemma, W perp is invariant under T star star, which is T. And we also have W perp. Okay, we have W is invariant under T. We also have W perp is invariant under T star. Because if Y is in W perp, right, Ty and En gives equal to T star Y En gives you Ten, Ten, and T of En is just some, right, some, wait a second, T star Y En, the Y is in W perp, Y is in W perp, so T star Y inner product with En gives you what is En? En is the normalized vector TV. Ten. Oh yeah, it is Tn. But no matter what, right, like this lambda En, we move it in front, gives you lambda bar of this, and Y is in W perp. Yeah, so this is equal to 0. I was confused by the bar here. But anyways, if Y is in W perp, then T star of Y and En are orthogonal, or perpendicular, so that T star Y is in W perp. Okay, we're good. So we have these two, and we also have those. Now we can see that because T is invariant, W bar is invariant under T, so we induced another operator that restricted on the W perp. And similarly, this is also invariant under T star. We have defined S naught, the induced operator by T star restricted on W perp. And now we have T naught and S naught. Okay, so for T naught and S naught, claim is that S naught is the adjoint of T naught. And the proof is by one line for any Y perp and W perp that is contained in V, right? T naught Y prime is equal to T Y prime, right? Because Y is, right? And we flip to here. Again, Y prime, and so we can change it to S naught Y prime. So we have this formula which shows that S naught is the adjoint of T naught. Now, since TT star is equal to T star T, since T is normal, we have that T naught is also normal. We have this as true, right? Because T naught S naught of Y is T naught of T star of Y, right? Because Y, right, we just restricted, so this is really equal to T star of Y. But remember, Y is in W perp, so W perp is invariant under T star, so this entire thing is again in W perp. Right, so T star is something in W perp, which is equal to T of this thing. And for this side, right, you just check it by yourself. It is similarly by symmetry. So we have that T naught is normal. Okay, what we see that is we can just apply the induction hypothesis, right? We just apply induction that we can find E1 to En minus 1 and lambda 1, lambda n minus 1, such that blah, 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 blah. And now, same as the case in the real, we just pass it back, right? We just do the exact same reasoning. Okay, and for the converse direction, if we have that, that means that T has a diagonal matrix with respect to some ONB of V. And with respect to the same ONB, the matrix of T star is the complex conjugate transpose, right, of the matrix, which is again a diagonal. Well, because diagonal matrices commutes. So T and T star commutes, which means that T is normal. And yeah, and this is everything for the complex spectral theorem. And I'll see you guys next time.